philosophy, I'll first talk about the complex field, and this will be things you already know, but I think it will be nice to write them down so that it's clear the analogy with it. Then I'll talk about the exponential function, which is kind of the main motivation for this area, and a bit more interesting than, I guess, the field. And then in the end I will talk about generic functions and what we know about them and what I've proven about them. Okay. Yeah, look, if you have any questions, you can ask them at any point. If you cannot see something on the board, let me know. Okay, so the first part is field. We're looking at the complex field. Structure. Right. So what are some things we know about it? Well, it's first order axiomatizable. It's just by the theory of the algebraic closed field superscript 0. Which of course means it's decidable. Then something that I guess Francisco mentioned during the course is that it has quantified elimination, which in particular means that if we take a formula in this form, so this is a formula in one variable with some parameters, then it's equivalent to a Boolean. Okay, how annoying this is the sound? I can change the. Okay, maybe the noise. I mean, it's a bit annoying to me, so maybe I should. Okay, this is better. The Boolean combination. Again, first order formulas, and in this case it will be just some polynomial over x equal to 0, where this is a polynomial over the field generated by these parameters. So A okay, in particular we know that these formulas define finite sets. Well, unless it's a trivial, it's actually a 0 polynomial, then it's just all of C, but which means that this formula has to define a finite or cofinite set, which is a property called minimality, so the structure is also minimal. Every definable subset is or cofinite. So here, definable always means with parameters.
You're just talking about one variable.
Yeah.
So when definable.
Yeah. And moreover, of course, this is true not only for the complex numbers, but for any algebraically closed field, which is 0. So, well, I guess not. It will need characteristic 0 as well. So that means that's the theory is strongly minimal. So every model is minimal. Model is minimal. Okay, what else do we have? What else do you want to mention?
What does that mean to say that it's minimal?
So minimal means structure is minimal if every definable subset is finite or cofinite.
Oh, okay,
that's the definition.
Okay.
Then the definition of a strongly minimal theory is a theory where every model is minimal. So for example, another thing is if we look at the monotheoretical algebraic closure in the theory, so what this closure does is you give it a subset, and then it gives you all the elements which are algebraic over the subset, meaning that there exists such a formula that this over the subset that you start with that this element satisfies and it only defines a finite set. So in this case, it will be conjunction disjunctions of these polynomials. And then that means this will be just the usual algebraic closure. So ACL is the field theoretic algebraic closure. And one of the properties of this closure I wanted to mention, which I guess right now is obvious, is has countable closure property. What does it mean? That means that if A is countable, then ACL of A is also countable. Right? So if you take a countable set and then you take its algebraic closure, you get a countable field. Okay, and the last thing I want to mention about field structure is that this theory is also uncountably categorical. Meaning that if you take an uncountable cardinal, then you have only one model of this theory up to isomorphism. And this is basically true because you choose a transcendental basis and then its cardinality defines what this field will be. So let's say characterized by okay. So this is all I wanted to recall about the field structure of the complex field. So the second part, exponential. So the idea here is, okay, this structure is really nice, has all these very nice properties. What happens if we add something to it which is also not that bad? For example, the exponential function. So we're looking at this structure in the end. And in general, I will write CF for this thing where I add a function f, so that I don't have to write all these things every time. Okay, so one thing you can do is you can look at its kernel. So this is a definable set, and that is 2 pi z. So we can already define something which is not finite or cofinite, so this definitely is not minimal. But what's much worse, you could play around with it a little bit and actually get all of the integers. So you can look at the set which would be the multiplicative kernel stabilizer. So all the numbers such that when you multiply the set by this number, you still get the same set. Okay, hope I wrote it the right way. And this is exactly the set of integers. So now you have integers together with additional multiplication, so you get all of first order arithmetic. Okay. And this is obviously very bad. So this structure cannot be axiomatized, it cannot be decidable, it cannot have all these nice properties that I wrote down. But there is still some hope. So Zilber produced this property called quasiminimality. Let me define it. The structure M is quasi-minimal. So this is just an analog of minimality, where okay, we know that we cannot define, we can define countable set, but maybe this is kind of all there is. So maybe all the definable subsets are countable or co-countable. But of course, this is a very kind of non-monotheoretical property, because if you take a structure which is quasi-minimal, you can always construct an elementary extension where you add elements so that this is not true anymore. So this is really a property of a structure, not of a theory, unlike this strongly minimality things. Okay, and what was conjectured? Zilber's conjecture, also known as Zilber's quasiminimality conjecture, because I guess he has more conjectures. So this was 1997. Is that this structure is this is kind of what Boris thought might mean that this structure is not as bad as we could have thought. So, for example, this would mean that the reals are not definable. Okay. I guess now I need to erase this.
Is this conjecture still open?
Yes, I will talk now about what are the ways to resolve it, and what is left to prove, to show it.
It somehow feels as if somebody should have proved it. Anyway,
That's what many people think, yes.
That's I think the feeling in modern theory too.
Okay. But it's
Okay, so what Boris did is he introduced this theory. I'll just write Tx. And since we cannot really talk about this in the first order language, this is actually a theory in a higher logic. So, okay, so this is so what we do is we now can use countable conjunctions and disjunctions. This was this omega-1 means, and this Q is a new quantifier which says there's uncountably many, so that we could actually talk about countability. So, for example, Qx of phi, Qx phi of x means there is uncountably many x's which satisfy phi. Okay, and so the theory consists of the following axioms. So you still have, of course, AC of 0. Then we want to say what we expect from the exponential. We expect it to be a homomorphism between the additive and the multiplicative subgroups. And moreover, the trick is surjective. Just like surjective. And then we also want to say that the kernel should look like infinite cyclic subgroup which is generated by something transcendental. It's something we could also say, but here we would need, of course, using countable disjunctions and conjunctions. So external is infinite cyclic group related incidental element. Okay, a bit more. So what was my order? Okay. Then we also add something like this countable closure property, but for another closure. So I'll write countable closure property. So here we need to use this Q, but instead of using the algebraic closure, we use this closure that, okay, just write it first, fourth closure defined by isolated so the analogy here is that here the algebraic numbers, you can also think of them as, I guess, zeros of field equations. So what you do here is you take systems of exponential equations, so they could also use the exponential, and then you also need this condition that the Jacobian is non-zero, and then the closure, you give it a set, and then it gives you isolated zeros of equations over that set. That's basically what's happening, but I don't think it's worth actually writing down this definition.
Each of these bullets is a collection of axioms in the L omega 1.
Yeah, this is collection of axioms. And so here you need to use Q to say that that if something is countable, then its closure will be countable. Okay, next one.
Does Q say there exist countably many or there exist uncountably?
Uncountably many. Well, I mean, it doesn't matter too much which one you choose. And I'm not going to actually use Q. I just wanted to be clear that this is actually
So the way you state the countable closure property as axioms, I mean you quantify over. You have. Here you had that A was the definable set, yeah.
No, A is just any subset.
Oh, any subset.
Yeah.
Oh, so how do you express this as an axiom?
Okay, that's a good question. No, I mean these equations. Okay, these equations only use finite. There's only finitely many coefficients. So you write for. But there's countably many actual systems of equations you could write. And then for each of these systems, you could write. So I guess what you actually do is write if A is finite, then the closure is countable, but it will be equivalent to this.
Okay.
Yeah. Okay, so this is Schanuel's conjecture is a famous non-theoretical conjecture, which kind of talks about what we expect the exponential to behave like with regard to algebraicity. So it says that if you have n q linearly independent numbers, then the standard degree of them together with their exponent Okay, maybe I'll write it on the over Q. Okay, can you see this? Okay, so yeah, so you just take n numbers and then you take their exponents and you expect the transcendence degree of this over Q to be at least n. And the reason you add this condition for them to be clearly independent is because as the exponent is a homomorphism, so it would take any Euler dependence between them into a multiplicative dependence between the exponents. So then it might be that accidentally you get a lower degree, but if that doesn't happen, you expect this to be true. And yeah, this is like this is a very strong conjecture, which unclear how to even I guess start with it. So one of the consequences of it is that E and pi are algebraically independent, because you could just put here 1 and 2 pi I, and then you would get here that yeah, it would be equivalent to E and pi being algebraically independent. Okay, and then the last axiom. Okay, maybe what you said. So one other kind of way to look at the Schanuel's conjecture is to think of this in terms of algebraic varieties. So for this, for example, means that since this point has transcendent degree at least n, that means it cannot belong to any variety of degree less than n, right? So this does not lie in V. So here V is some algebraic variety over here of dimension less than n. So this last axiom I'm going to write is kind of opposite of this one. So instead of saying, oh, when do points of this form do not lie on an algebraic variety, it will say when do they belong to algebraic variety. So 4, 3, irreducible. Okay, so you start with some algebraic variety, which lies in this product of f to the power of n and its multiplicative group to the power of n. Free in the return, I don't want to actually write down what it means, but free means that this variety, if you project it to any of these coordinates, will not lie in a variety defined by a Q-linear equation, dependency, or if it's here, then the analogous thing with multiplicative. So it kind of corresponds to this condition. And then return means that if you act on it with by integer matrices, then also the dimension shouldn't suddenly go down when you don't expect it. So kind of some conditions on this V being not some weird thing that suddenly interferes with the structure of the exponential. And then when you take the such a variety of dimension n, then you intersect it with the graph of the exponent, by which I mean points of this form. Then this should not just have points, but actually have generic points.
So having generic points, I mean that there's a point whose Zariski closure in the variety in affine space cross multiplicative group to the n over Q is the whole thing?
Yeah.
Okay.
I mean, also, it's not very important today what this means. But it is... If someone else didn't understand that, it's fine. Okay, so so Zilber introduced this theory, and what has he shown about it? Okay. So this theory is also uncountable and categorical. And moreover, all its models are quasi-minimal. So in some sense, this is like a good analog of what we've seen in the field case, because you also get these nice things analogous to what we had before. And then, if we knew that the complex exponential field satisfies all these axioms, then we would know that it's quasi-minimal, and moreover, we would kind of know that. We would know that this is actually what defines the complex exponential field, because it is the only one that satisfies all these axioms. So this, in some sense, it's right. This is the right theory for it. But of course, so another thing that Zilber did is he proved countable closure property. So the first part of axioms are trivial, and then the second one, the countable closure property, turned out not to be too difficult. So I'll just write CCP. That means countable closure property.
Can I ask you a question? So TX consists of everything on that board, is that right?
Yeah, but this board is exactly the...
So all those things are part of the axioms.
Yeah.
Okay, and when you in one of these models with TX, does Q always? I mean, Q there is just a symbol, but I mean, you are thinking of it as being there exists. I mean, that it holds something for. I mean, does the interpretation of Q in every model tell you that?
Yes.
Tell you
Yeah.
that it's on this.
Yeah. So Q is not part of the interpretation. Q is kind of this logic we're working in.
Yeah. Okay. So it's not obvious even that Q has the meaning that was intended for. Is that what you're saying?
No, I'm saying the opposite. That's it's always this. It always has the same meaning. We're not defining Q.
Right?
Mm-hmm.
It's a quantifier, right?
Yes, quantifier.
It says it exists countably many.
Okay.
The confusion is maybe that it's like not part of the language, as you would say in model theory. It's more part of the logical symbols, not of the like functional relation symbols.
Okay.
Yeah.
So you're saying that by definition, it always means.
Yeah. Just like the quantifier exists always means exists.
Okay.
Never means anything else. Does that make sense?
Yeah, I think so. Yeah.
Okay.
Excuse me. Also for the EAC, I think so. Once you establish that all intersection have all these things have intersection, then there must be generic points in the intersection. Is that right? So you can deduce from having intersection to having generic intersection.
I think so. Yes. Yes.
So that makes this EAC first order.
Yeah, I think so.
Can I ask one more question about the Q?
Mm-hmm.
So, if I take if I take something like the natural numbers, and then it's kind of silly to have the q because everything's countable. But I could put the q in there anyway, and then if I take the alter powers of that, then now the q is it just no longer true that said instances will be can be transferred to the alter powers? That's only for first order, and this is no longer first order. Is that what?
Yeah.
Okay.
But I'm not a big expert on. I cannot tell you what does still hold there and what does not.
I had another question about that actually. Maybe you know that one. So in first order logic, you have this theorem that says categorical implies complete. Is that at least true here?
No. Okay. What was I talking about? Oh yeah. Okay. So Zilber showed that that Schanuel closure property holds for the complex exponential field. He did this through external theorem that I think Sebastian was talking about during his course, and I will also write it in a second. So then we know the first two things. The only thing left to show is the Schanuel's conjecture and the strong exponential algebraic closeness. So then, if we would show these two things, they would imply quasiminimality. So for okay. But of course, the Schanuel's conjecture kind of is a bit too difficult for this to be done. So what's a bit better news is there's a more recent result of Martin Bates and Jonathan Kirby from 2018, where they kind of took this approach, and they managed to, by working over, not over Q, but over some other field, to somehow hide the Schanuel conjecture into that. So what they got is that exponential algebraic closeness quasiminimality. So here, exactly by exponential algebraic closeness, I mean the version of this where you don't ask for points to be generic, you just want there to be points. So this holds for TX, but actually the result is a bit more generic. So you could also do this for things which are some way similar to the structure. So more. But that's why kind of currently people are mostly working on this exponential algebraic closeness, and there's a lot of things done kind of doing this in some particular cases, like n=1, or when one of the projections is nice enough, and things like this.
So this quasi-minimality is in the stronger language, right? So any definable set in the stronger language, it's also countable.
That's a good question. Yes, I think. Yeah, I think so. Yes, definitely. Yeah, this would even be true like sets which are closed under automorphisms are countable or co-countable. So yes. Okay, and before moving to generic functions, I just wanted to say a couple of words about Schanuel theorem. So okay, I'll just write it here. So some people call it access theorem. I just kind of wanted to emphasize its connection to Schanuel's conjecture. So it's I'll give two equivalent formulations, where I think the first see that it's kind of like a Schanuel's conjecture, but for power series, and the second one is more geometric, so it's more in this language of varieties, and it will be important later. Okay, so the first formulation, if take n power series is without a constant are linearly independent, then okay, so you take n q-linearly dependent power series without the constant term, and you also take their exponents. And but now you're looking percentage degree not over q, but over the field of rational functions over this t, and then you manage to get this bound on the percentage degree. And the equivalent geometric formulation once again, you start with an irreducible algebraic variety, and U, which is maybe not the whole intersection, but some analytic component of it. So what do you expect its dimension to be? You expect it. So you take something, you take V and you intersect it with something of dimension n. So you expect the dimension to go down by n. You expect this to be not more than dimension z minus n. And this indeed happens unless, again, you have some of these q-linear dependencies on u. So unless the projection of q to this additive side, to Cn, is contained by so unless there is some q-linear dependency on the additive side of u, which is also the same as saying multiplicative dependencies on the other side. Okay. So you will see later why I actually wrote this down. Okay, so now finally I can talk about generic functions. Okay, so the idea here is we see what happens with the exponential. What happens if we add some, instead of exponential, we try to add some other function, let's say holomorphic on the whole plane. Of course, in the case when it's a polynomial, you haven't actually done anything. And all the other cases, turns out that this question is still, like whether you get a quasi-minimal structure is still very relevant. And so far people kind of expect things to be quasi-minimal, but there's no lot of examples when you can actually prove it. And this is kind of the only example which you have. And the idea behind it is you kind of have something like this theory, but you simplify it so that it actually fits first order language. And then you kind of, instead of looking at an already known function, you kind of build up a function which would definitely satisfy something like this. So this theory of I'll just call it theory. This is just a first order theory in the language of fields with a function in it. Again, start with when plus field is 0, and then you just have a function on this field. You don't ask anything of this function. You don't want it to have any real structure on it. And then you have something called Schanuel's property. So this is an analog of the Schanuel's conjecture, but since we don't want to have any structure, we kind of expect it to be very transcendental. So if you have numbers which are distinct, then tendensively so you do exactly the same thing. You take numbers with their images, but now the only thing that our function is preserving is that, okay, if two of our numbers would be the same, then of course their images have to be the same. But there's no other algebraic dependency between them should be preserved. So for example, if you take all these numbers to be algebraic, then their images should be all transcendentally independent. Okay, and the second. So this is an analog of the exponential algebraic closeness. We call it existential closeness because it's existential closeness with respect to certain embeddings. So this is not literally existential closeness in the usual model theoretical sense. Okay, such that So you start again with the algebraic variety. I'll explain what free and abroad means in a second. But now you don't have this. You don't need to write here multiplicative group. You just have fn times fn, and then it's defined over some finite tuple. So I'll just call it C. There are again all be distinct, and moreover, they should not belong to this tuple we're defined over. And then image. Okay, so yes, you take this variety, and then there should be a point of the form, which lies in the graph of G, and we also ask the points to be distinct and not belong to the tuple we defined over. Okay, I'll also say what free and broad means. So free here doesn't mean the same as free there. So it's just same name because it corresponds to the same idea. So we used to say that free means that the projections do not belong to, they're not Q-linearly dependent. Now we don't care about Q dependencies, we only care when things are distinct. So free means that it is not contained in a variety defined by constant. And here by xi I mean the coordinates on the first part. So I call these coordinates I call xi's and these I call y1. Okay. And broad just means that
we need some dimension conditions on the variety it's contained in. Otherwise, I can just take 0 of those equations and get the whole set.
No, I mean, shouldn't it be possible that you take one of such equation and the variety, it holds on all the variety?
Okay, so we need to be not of dimension n.
What do you mean?
You mean at least one equation?
Yes,
That's
yes.
a dimension requirement. Another one than I thought, but
Okay, so for broadness, what you do is you pick some of the xi's and then you take the same yy's and you project them to them, and you want the dimension not to go too much down. So for any, you choose numbers between 1 and n. The projection of B onto x1, x2, 1, okay, has dimension not smaller than k. So you project to 2k coordinates correspondingly these n-dimensional variety, and you want the dimension to at least be at least k. Okay, so this is all of the theories. It's just these three axioms. This was also introduced by Zilber in 2002.
Maybe you said this already. What was the C bar?
It's just a finite tuple that this variety is defined.
Oh, that's a C.
Over.
Oh, sorry. It looks like a Z. Okay, never mind.
Okay, yes. So what he has shown is that this theory is consistent and complete. So this is done using this Khrushchevsky's amalgamation construction. Then it's also omega stable, meaning that there's countable many types over countable many parameters, and this implies that the theory is really nice, and it definitely does not define integers. It's much better than what was happening with the financial case. And it also has quantifier elimination, but not in its original language, but you need to add some formulas. So up to these formulas that I will write psi v, which say, let's say it's okay, and they say there exists such that, okay, maybe I should write them on the next. Such that they're all distinct and so it's kind of formulas corresponding to this existential closeness property, and you have one of these for free and broad, irreducible varieties of dimension over Q. Okay, so once you add these formulas to your language, then you get quantifier elimination. Okay, but then there was still a question of whether there are any such functions on the complex field. So this is what I'm going to talk about now.
Excuse me. The free of this variety is only required for the first n coordinates, or
yeah, for the first n coordinates.
You only need the requirement for first n coordinate.
Can you say it again?
You only need the requirement for first n coordinate.
Yes.
But what if, let's say, the dimension concentrates on the first n coordinates? Your variety says the last n coordinate equal to a constant.
Yeah.
And
what's...
Then I should not expect this to have a solution.
Why?
G is subjective. G is supposed to be subjective, right? I think that's...
Yes.
Oh, okay.
Okay, yeah, so Alex Wilkie came up with this construction of a holomorphic function that would actually satisfy all of this on the complex field. So what he did, this was 2005. Okay, so the first thing he did is he added this condition he needed of that our function should be 0 at 0. So this contradicts the Schanuel property. I need to literally use this theory, but you can just modify it a little bit. So you add here 0, 0 equals 0. And here you need to add that they are also all non-zero. And also here that they also are non-zero, and here as well. So you get a bit like formally different theory, but then everything goes through. You just need to always kind of take care of zero at the same time. And then having this modification, okay, he constructed what he called Liouville functions. So this name comes from Liouville numbers, which are I misspelled Liouville. No, I did misspell it. There should be a U. Okay, great. So these numbers, which are kind of the easiest examples of transcendental numbers you could construct, with the idea that you take a number where in its decimal form the coefficients go down very fast, so they're kind of easily approximated by rationals, and that cannot happen to algebraic numbers. So for example, the Liouville constant is the number where it has zeros everywhere besides factorial places. Okay, so this analogy, what are the Liouville functions? You try their power series. There's a power series. Here, as I said, we want the constant term to be 0, so it's 0, 0 is indeed 0, where ANs are non-zero integers, such that for any k, with n, these inverses of the coefficients should increase faster than any power of n. So then these functions are well approximated by polynomials. So this function kind of has to be very transcendental, and then you can show that it satisfies Schanuel's property. So you show that if you add such a function to complex field, it satisfies Schanuel's property. And then when he was trying to show the existential closeness, he managed to do it for the case when the tuple is empty. Kind of be working over rationals. And then later, I think the same year actually, Oiran managed to finish this proof and show that it holds for NEC. And then he also showed that actually this theory is the same theory as his introduced theory of limit polynomials. But I guess I'm not going to talk about that. Okay, so at least we know that these functions are somewhat relevant to the complex field. They do exist. What I have done is first let G generic. So by generic function, I just mean a function which you add to the complex field, and you get a model of this theory. Homomorphic function. The structure is quasi-minimal. So in particular, this is true for the Zilber functions. And second, if we have two of these, so if you have two of them, then actually the structures you get when you add them to the complex field are isomorphic. So in some sense, it doesn't really matter which function you choose. So you might as well, for example, if you want, choose this Zilber function, or one of these Zilber functions. Okay, now I wanted to have say a couple of words about the proof, but I guess, okay, I'll try to be quick. And I'm going to connect this also to this actual proof ideas. Maybe I'll talk more than write for the sake of time. Okay, so how did we show minimality in the case of the field structure? We had quantifier elimination, and that was enough to show that these quantifier-free formulas define finite sets. So here we also have quantifier elimination, so it's enough to show that these psi v's define countable sets when they're over one variable, so define countable sets. So that's what we need to show. And this is actually also equivalent to this countable closure property for a certain closure. For example, yeah, I mean, one way to define it would be just to say closure of a set is everything that such formulas can define, and then it would be equivalent. And then you can also see kind of where is this countable closure property hiding. So you know how in the exponential case we had, if we know in the exponential case, we knew that if we have countable closure property, Schanuel conjecture, and strong exponential algebraic closeness, we could get quasiminimality. And then for the exponential case, we could prove this, but we cannot do anything with these two. And here we kind of start with a function which already has something like this. So naturally, this only missing part is something like countable closure property. So this is also the analogy I want to show. Okay, and this countable closure property is just like in the case of exponential, where Zilber used axiomal theorem. You can also use like the analog of the axiomal theorem. So then the idea is you take the, so as we know, Schanuel's theorem is kind of a weaker Schanuel's conjecture. So the idea is you take what we already know, the Schanuel's property, we already have a very strong property. Then from here we deduce Schanuel for this generic function. And then from here we use something like what Zilber did, and we deduce countable closure property. Okay, so what is Schanuel for generic function? Well, I still have the, so you write exactly the same thing, but then instead of the projections being contained in some rational dependency, you just once again replace it with just xi equals xj. And then this proof goes like this. You take any function which satisfies the Schanuel property, so you actually don't need this existential closeness at all. And then you use kind of complex geometrical methods. So you know it's holomorphic, and then you can take some. If you know if this dimension is bigger than dimension of d minus n, you can take neighborhoods and find an algebraic point there. And then if you're careful enough, you can show that this algebraic point will kind of push the dimension down, and then you will get contradiction with the Schanuel's property. So this is basically the idea behind this one. And then here what you do is, so this is just showing that psi v defines a countable set, and you do it by showing that these points you get here are isolated. So you can only have countably many of them. And you show that they're isolated exactly by, you put dimension v is equal to n, so then dimension of u has to be smaller or equal to 0. So that's an isolated point. So kind of, I guess I'm just saying this, how here kind of suddenly have all of these things coming together in some sense. Okay, and for the categoricity, what you do is you kind of show that you can also do something similar to what we did in the field case. So there we had transcendence basis, and here we would have these what I call GCL independent sets. So GCL is exactly this closure that you get using these formulas, and then you show that a model has kind of a closure property exactly when it's prime over such set. So then if we already know that these things have countable closure property, then they should be prime over these independent sets of size continuum, and then just like in the field case, that kind of defines them. Yeah, that's why they're isomorphic. Okay, that's it.